crystal samples. The other problem is the microwave nonlinearity that Alex has talked about yesterday. And there is actually some the theoretical calculation on the impact of having two gaps on the nonlinearity in magnesium diboride. The conclusion is that having two gaps actually is not good for the nonlinearity of these materials, and it's larger than a superconductor, let's say, with one single gap of 40 Kelvin. So if you look at this plot, this parameter B it represents the nonlinearity as a function of temperature. You see that if it is just if it's just a superconductor with a sigma band, you will see a curve like that. But if you have a superconductor just the pi band, you will get this curve. And altogether, there is this big shoulder for the nonlinearity for magnesium diboride at lower temperature. And this plot, it compared this parameter for magnesium diboride, that's this solid line, and YBCO, that is this dashed line. It is known that for YBCO, the nonlinearity actually become worse at low temperature because of the D wave pairing symmetry. And this line, again, is a BCS superconductor with TC equals to 40 Kelvin, which is just for comparison. So at low temperature, it is better than YBCO, although you do have this shoulder. That's the bad news. The good news is that actually you can tune this nonlinearity by tuning the relative cleanness of the two bands. This plot showing these curves that correspond to different situations where in some situation the pi band is dirtier, in some situation the sigma band is dirtier. And when you do that, you can change the characteristics of the temperature dependence of the nonlinearity. So you could adjust it so that you could have a lower nonlinearity in some of the temperatures. So this again is something that needs to be studied to completely understand the nonlinearity behavior. In our case, we have collaborated with the group at the University of Naples to measure the nonlinearity in our films. And so this result shows the result of YBCO, and also this is the theoretical curve. As I mentioned earlier, at lower temperature, it actually takes off. And so here are the data for niobium. And this triangle is for magnesium diboride. And so it actually can be fitted to a situation where the scattering, the gamma pi over gamma sigma, so this is the relative scattering between the pi band and the sigma band, equals to 2, then the data can be fitted reasonably well. So this is just it's just one data point, but we can see that by modification of the interband and intraband scattering, we can have some handle on the nonlinearity of magnesium diboride. These are the reasons that why we think magnesium diboride is interesting. And also, if you put it together with other superconductors, niobium is the one that we would love to replace. And of course, the magnesium diboride has much higher TC. And so the gap is higher. And also, if you compare the penetration depths of all these different kind of superconductors, you find that magnesium diboride actually has the smaller the penetration depths among all these superconductors comparable to that of niobium. And the other advantage, as I mentioned, is the residual resistivity, which is the lowest among all these superconductors that could be considered for RF applications. So magnesium diboride is interesting, and it's also we can also fabricate high quality of the thin films. And here are just some result of the thermodynamic calculations. This pressure versus temperature diagram is what we often use to guess what is the good conditions for depositing any films, actually. So here are some keys to the growth of MgB2 film. First, from thermodynamic calculation, we find that we need to have a very high magnesium vapor pressure during the growth to keep magnesium diboride phase thermodynamically stable. This is one of the biggest problems early on when people are trying to grow these materials. It's very high, so it poses a big technical difficulties. There is an advantage for magnesium diboride. You can see from this phase diagram that they are the so-called line compounds. So in these kind of materials, you do not have to control the composition of that, because as long as you have the composition within this range, for example, you always get, in this range, you always get magnesium diboride plus some of the other gas phases. So during the deposition, you have to make sure you provide enough magnesium. And then whether magnesium is too much or not, it does not matter, because the extra magnesium is in the gas phase, you just pump them away. The other important keys are the oxygen. You have to keep oxygen away, because the magnesium reacts very strongly with oxygen, and it can form MgO in the film, or it can deplete the magnesium vapor pressure. Those are harmful. The other thing you have to worry about is to avoid carbon, because carbon is the impurity in these materials and also suppress the superconducting properties of magnesium diboride. In my lab, we use this technique. We call it hybrid physical-chemical vapor deposition. It's basically a CVD process. We use diborane as the source of magnesium, as a source of boron. But for magnesium, we just use bulk magnesium and heat it together with the substrate. And the total pressure is fairly high, like, for example, 100 torr. So that make it possible to generate high magnesium vapor around the substrate. And then when we heat it up, we have this high magnesium vapor. Then diborane comes and decomposes, and we can form film on the substrate. And the whole process is similar to those that people use to grow semiconductors in a sense that it really avoids the oxidation in this process. Like the hydrogen carrier gas, and very pure source of boron, and very pure source of magnesium. So those are the factors that allow us to make a very, very clean films. This is the best result we've obtained in terms of how clean the materials is. And we have the residual resistivity below 0.1 micron centimeter. So this will give a very large, a quite large triple R, and TC is about 40 Kelvin. And I've shown some of this data. So if we look at the surface resistance, because of the low resistivity, we got low surface resistance, we got short coherence length, and actually also we got a smaller energy gap. That is because by making it clean, we reduce the coupling between the two bands. In microwave measurement, what we see is this 2 MeV gap. We don't see that of the 7 MeV gap. If the materials is dirtier, actually it promotes the coupling between the two bands. Gap can become a little bit higher. That might be something interesting for this application, but that needs to be studied further. There are other successful techniques that we've heard a lot about the technique from STI, and I'm sure Xiaoxing is going to talk about that. In their case, they are able to produce a high magnesium vapor pressure by connecting this to a magnesium furnace, and boron is by the E-beam evaporation. And for the reason that we discussed a little bit earlier in the morning, they can drive out the oxygen in this pocket, ensuring that you get a film which does not have a lot of oxygen. So this is their published data. They can get high TC and residual resistivity about 2 micron centimeter. And I've seen presentations by Brian. They can get like a 1 micron centimeter range. And so this is quite successful in making very good films. And we have used the STI heater also in the mode of doing CVD. Like instead of E-beam evaporation of boron, we just use diboron as a boron source. Of course, the whole environment, we are not using vacuum. We are using hydrogen in the whole process. And that make it even cleaner process. And we get like a 1 micron centimeter residual resistivity and TC of over 40 Kelvin. So this is indeed a very nice approach in making MGB2 films. There are other ways that you can do it. I'm not going to talk about every one of them, but I want to mention this axial annealing process. That is, you can first deposit boron films on the substrate, and then anneal this film, boron films, in magnesium vapor at high temperature. And this way also, using this way, you can get epitaxial film with very good property in these films. So in the thermodynamic phase diagram, actually, you again are operating at a high magnesium pressure and high temperature regime. And in our lab, we have done this by depositing boron film using a CVD process, and then annealed it in magnesium, and we can get a residual resistivity around 1 micron centimeter and over 40 Kelvin TC. So this is another approach that one can use to make high quality films. So that's the first part of it, why we are interested in using MGB2 for RF. And the second part, I will talk about the progress report about our own research. So we have a project ongoing that is supported by the High Energy Physics Office at DOE. And the project started in June 15th of this year. So we just barely got this process started. And our objective is to develop this HPCVD technology for MGB2 SRF cavities. And so there are two research activities that we promise to do. One is to study the properties of MGB2 films that is related to the applications for RF cavities. And the other research area of research activity is to coat single-cell RF cavities with magnesium diboride films. In the proposal, actually, we promised to coat cavities that will be provided by collaborators in other labs. But the later that we found that, so if we talk about coating cavities, we will first coat the 6 gigahertz cavity that's provided by ANSO here, because it's smaller, it's easier. We don't have to build a new setup. We can use existing setup to coat it. But of course, if we are successful, we are going to try to coat larger cavities that is provided by other collaborators. In the film area, we'll be depositing large area 2-inch or maybe even 4-inch diameter films, and then study all these properties that are important for cavity applications. So first off, in terms of